Welcome to the course Algorithmic Design, session 4, Flow. In the textbook that I gave you, this mathematical principles of computational design, there's a section called particles and forces, or that's actually a chapter, particles and forces, and there you have Navier-Stokes equations explained. So that's kind of, those equations are used to really to simulate like proper fluid flow, incompressible fluid flow. But here we are not doing that because implementation of these Navier-Stokes equations, so to do basically computational fluid dynamics, that's quite a hard topic. So it's not, we are just not doing it. But we are going to look at some other types of sort of flow in that we can sort of simulate very easily, let's say in Rhino. And basically the one that we will look today in some abstract ways, it's called gradient descent. So that's on this picture here. Gradient descent is basically if I have a field or a vector field, or in this case, this is actually just a scalar field. So I have kind of number associated with every point in space, and then I can calculate the gradient in a way. I can calculate it directly or sort of indirectly. But this gradient basically shows me like I can in a way move particles in that way down the gradient or up the gradient. Or so gradient is basically guiding my particles, and that's a little bit what you already did last time. There was some gradient in our vector field, and that gradient we didn't really see it, but sort of there were vectors there, and vectors kind of in a way define that gradient. But I can also define it in different ways, for example through a height map, which we will do today. And yeah, there are some other kind of resources here. Kind of why is that flow sort of interesting in the context of design? And kind of sort of maybe landscape architecture. It's because we can use flow, of course, or gradient descent to simulate rainwater, rain flow. And there are some different theories about kind of then how this sort of liquid flow down the terrain, and then including erosion. So the material is also kind of flowing down the terrain, but also taking away the pieces of terrain or granulate or aggregate that the terrain is made of, and then how these channels and their formed. So there are different theories, like physical theories, basically how this is created, and they're all related a little bit to sort of self-organization of matter and kind of basically water trying to find the most optimal flow or so. And these kind of patterns then give us erosion patterns or in the terrain, and also the height map that I'll show you later, which is the terrain. It kind of looks a little bit like this, or it looks like it was kind of eroded by water over many centuries. Then kind of jumping scales, or jumping in. This is actually a leaf, or so somehow it turns out that these flow problems are related to. It's actually explained here. Yeah, they're related to this problem of reachability. Or so I have a surface, and I have a linear element, in this case a vein of a leaf. I'm trying to reach with this linear element every or as many surface elements of that leaf. And this is again related to this reachability problem, which is basically how to get the nutrients, how to create a network of veins that delivers nutrients to basically every cell in the leaf. And in order to do that the most efficiently, the nature kind of is using fractal structures. So this kind of self-similar branching structures, which we will look also closer next time at the next lecture. But somehow these fractals ordering and the flow or problem kind of issues of reachability, they're somehow related. So here I kind of connected just kind of a physical water erosion with basically how maybe the veins in a leaf are organized. This is valid also for other tissues like flesh, like human body. Our veins, like our blood veins, work exactly the same way, except that we are volumetric, or we have volume, and leaves are more like kind of flat because they're optimized to catch sunlight, so they're flat. And then again similar problems in urban settings. So this is this one here example, like street network. I didn't actually put a reference here, but this is Sana'a city in Yemen, which is one of the oldest continuously settled cities in the world. In a way, kind of example of vernacular architecture, where basically the buildings were kind of added step by step, and then somehow the paths were, or streets were created to sort of make every building reachable, or so you can kind of go from the entrance of your building to the small streets, to the bigger street, to basically the main streets, main arteries. Or so it's here again we have the same problem of reachability like in the leaf. I have to be able to get from my house basically out of the city, or it would not be good if there would be a network of streets that were somehow cut off from the rest of the city, or so I have to be able to reach from any point in the city and the other point in the city, or so everything has to be connected, but then again in an efficient way. So here you have kind of an urban problem of reachability in urban networks, and here on the left you have problem of reachability in basically plant tissue. Okay, so these topics are somehow connected. Not to go too much into that. One of the first example that we'll do today is flow down the terrain. And this, unfortunately, these pictures are very small, but you'll see how it looks like in Rhino. So we will start with the height map. So this is a terrain height map, meaning this is just a grayscale image. And it's an example of a scalar field. Or so there's a point, there are different points, there's a grid with points, and every point has an associated number with it. And specifically, this number here is represented as a grayscale value. And because it's a grayscale image, we can have only 256 different grayscale values. So we have 256 numbers. And then these 256 numbers represent that many levels. So I can have 256 different height levels. As you know, if I want to show kind of the a whole Earth, this is not enough, or because if one level is 1 meter, that means I could only show terrain that is up to 256 meter high, which is not enough, obviously, not even for a relatively low country like Finland. But maybe for some terrain sections, this is usually enough. And this is, for example, used in games a lot, like entertainment industry kind of games. These height maps are then usually enough. And I guess you can also ramp these numbers up. But we are using this kind of, what is that? That's an 8-bit representation. And then, so this is basically flat, or so this is a flat, flat image, but it contains extra information, which we can turn into spatial information. So we can attach height to every scale, to every grayscale value. And we can choose, in this case, I think it's black is low and white is high. And then we can basically get a terrain from that, or basically any other image. But in this case, we kind of encoded terrain in this height map. That's why it's called a height map. And in Rhino, we'll then recreate this using a point cloud. So point cloud is basically recreates a geometry with points, and we will do it in a way that is fast, because if you do it with individual points in Rhino, it will be quite slow. But if you use this point cloud object, then it'll be faster, and we can also color individual pixels. Yeah, so I'll show you some tricks with that. So we can work with these point clouds, and then we can also simulate in a way rain flow. So again, this is very slow, very small, but basically we can put particles on top of this terrain, and we can make them go downhill. They are basically following this gradient, or so that just means particle is locally following, or it's going to the lowest point, or so it just looks locally what is the lowest point and goes there. And that's the first step. And then basically that's how kind of water flows down the terrain. It always goes in the direction, well, in the direction of the steepest incline, which is also the direction of the gradient. And we can sort of approximate it by basically saying it's going to the locally lowest point. And this will be kind of good enough for us. And we'll do maybe a similar example also one other time in the course, where we can also simulate the amount of water kind of going down. Here is just sort of a direction. Okay, then another example that we'll look today is Perlin noise. So I didn't put a lot of examples, unfortunately, here. Perlin noise is used. Perlin noise is, I didn't even write what the Perlin noise is here. I should have written it. it's basically this what you see on the left. So it is a type of I mean noise. It's like an image that is random but has a certain regularity in it, and it's useful because it turns out that many structures in the physical world, you can kind of create them by using this Perlin noise. Also, for example, the the bark of trees, certain kind of how maybe grasses are distributed in a kind of meadow. Certain other structures, they can all be sort of described by using this Perlin noise, which is just a mathematical principle of basically it's a mathematical noise. Also, we can generate in a computer. There's literally a certain algorithm that we can do it, and we can do it in 1D. This is a 2D. We can do it also in 3D. So we can basically use it to simulate quickly, not simulate, but kind of create structures that look a little bit like fog or mist or clouds. And because this algorithm has been optimized now for, I guess, since the beginning of the 90s, or I guess maybe end of 80s, when it was first invented, it is very fast. So it's again used in again entertainment industry, in games. So every time in a game, when you see sometimes when you see kind of a mist structure that is kind of rendered real time, very probably kind of Perlin noise is behind it, or it's that we cannot really simulate actual. It's very hard to do, or very slow to do, kind of real sort of fog and mist kind of a kind of fluid gas simulations in real time. So Perlin noise is a good approximation of that, and we will be creating then specifically again a kind of undulating surface using that noise, where we will interpret this noise as a height map. So we can get basically these two are the same principles are. So this is the height map of this structure here, or this surface, and this is a height map of this terrain here. And yeah, I mean, we cannot really animate it, but if you would use, for example, processing, we could do animations, and then we could even use these undulations to make this. You can make this surface sort of look like it's waving on the wind, or so you can kind of simulate a little bit kind of a wind. Kind of fabric in the wind. Or so again, we are not really simulating the interaction between the membrane and some kind of wind with turbulence, but we are just sort of approximating it using a Perlin noise, which just looks good enough, and it's much faster to calculate. And yeah, we can also use Perlin noise to kind of different kind of flow simulations on top. So this is one example here, which I'm not sure if we'll have time to do today, but it's for sure, a possible small project, one of these mini projects that you can do for the end. Okay, and then I think this is the last example that we look today. Last time I talked about metaballs, but I didn't really show them. So today we'll have a look at kind of metaballs, so like a simple metaball script, and we will again be using a grid to show basically this sort of metaball influence. Which are basically sort of like simulation. We can think of them almost like charges in space, and they're like attractors, or so they change the underlying geometry based on proximity, and their effects are cumulative, and they're kind of reverse proportional to the distance of the charge. So there's the so here we have different points, and they have different charges and different strength in a way, and the influence is kind of add up when they're closer together, and of course their influence in a way dissipates the further you are from the charge. And here on the bottom we have the same thing, but here we're doing culling, or so we are culling the areas with the highest charge and the lowest charge. So we are just in a way showing areas that have a similar charge, and that's basically what metaballs in a way are. They are just surfaces that connect areas with the same charge or same influence. But here we cannot really work with sort of thin lines because we discretized everything in points, or yeah, these circles. So we kind of work with sort of these patches. Okay, so these scripts we will look at. And as always, two texts to read from our text collection. I was a bit at odds. I didn't really know what to kind of which ones to choose, and So yeah, that's a bit kind of my just arbitrary choice, but I kind of decided to give you this some from Patrick Schumacher. He wrote in 2009 this very bit controversial book called the I don't even know how to pronounce this, autopoiesis of architecture. So autopoiesis is, it is, you can translate it as self-expression, or so in a way the theory that kind of life is self-expressing, or it's or kind of a living things are self-expressing because they are kind of you know, contained, and they develop, they grow, they multiply, and so on. So in a way, some similar ideas kind of we can apply maybe to architecture or design when we look at it in the context of algorithmic design. And Schumacher, of course, look at it from the perspective of parametric design. So he calls it kind of the parametric style, parametricism. So those are the terms that he uses. I would use more like algorithmic design, generative design in that context. Okay, and his text is from this book. It's actually quite a long book. There are, I think, 2 volumes. But there's one text called Key Innovations, Space, Place, and Field. So yeah, kind of goes a little bit also in the history of modernism. Some of these kind of concepts, how they were used in the 20th century, and how in a way the space and place were concepts used by modernists 100 years ago. And today, in the context of computational design, we would use a concept of a field. So that's, of course, directly relates to the text that I gave you last week from Stan Allen, field conditions. Or so somehow this field is a concept kind of that is used by architects and theoreticians, at least in this field. Okay, and then the other one is a bit older text from '93, but quite influential, from Greg Lynn, Architectural Curvilinearity, the Folded, the Pliant, and the Subtle. This is kind of a reprint of that text that came out from, or it was published in a AD called Folding in Architecture. I think, yeah, that was '93. And that, so edition of AD magazine. So that's not this one, it's just a reader that reprinted the same text, but that AD called, or with the title of Folding in Architecture, that one was quite influential. So because it basically introduced many key concepts kind of in the 90s in the artificial discourse. For example, the idea of kind of deconstruction was kind of first really well sort of explained and connected to maybe some ideas of Deleuze and Guattari in those texts first. Also, Greg Lynn wrote about that, and that's why it's in a way almost, I guess, what is that, almost 30 years old text, but it's still, I think it still bears some relevance, especially in the context of, again, kind of NURBS surfaces, flow, and so on.